MRI stands for magnetic resonance imaging and uses magnetic fields and radio frequencies instead of ionizing radiation used in X-rays to create an accurate image of the body. The magnetic field strength of an MRI, measured in Tesla, varies from 0.2 to 3 Teslas, which produces a very strong magnetic field. An electromagnet of this strength is capable of picking up a car. For decades, magnetic resonance, which was developed by Felix Bloch and Edward Purcell, was used mainly for studying the chemical structures of substances, and it wasn't until 1971 where magnetic resonance techniques were developed to be used on the human body. Lobauteur, Mansfield, and Damadian were the three big physicists of the 70s to really make consequent advances in MRI technology. Although Damadian was credited for having the first patient MRI technology, Lobauteur and Mansfield focused on techniques to produce 2D and 3D MRI images and won the Nobel Prize in Physiology and Medicine in 2003. The components of an MRI include primary magnets, gradient magnets, radio frequency coils, and a computer system.
Now moving to the basic principle. The human body is mostly water, so there will be lots of hydrogen atoms. The nucleus of every hydrogen is a proton that spins around its own axis, which are randomly oriented. Now if we apply a strong magnetic field to these protons, then these axes of the protons will be realigned along the magnetic field. However, some protons will be realigned in the opposite direction to the magnetic field, and these oppositely aligned protons will be targeted by the MRI scanner. When the radio frequency coil is turned on, the unmatched protons absorb the energy of the RF waves, flipping their axis along the magnetic field. When the coil is off, the protons flip back to their original alignment and emits energy in the way of signals back to the coil. These signals will be sent back to the computer to be analyzed.
The protons return to its rest state in different rates, which is why it's possible to identify different parts of the body and foreign growths like tumors inside of the body. Example, like muscle and fat have different rates because of the water content. Multiple transmitted radio frequency pulses can be used to identify tissues or size of abnormalities, location more precisely. A lot of infections or diseases tend to have a higher density of water, so if a higher water content is detected in a part of the body where there normally should not be one, it can be used as a good indicator that an infection might be occurring and a procedure can be done.
Based on the technology called nuclear magnetic resonance spectroscopy, which is used for the study of material science, MRI was developed. This technology can be widely used for the body with nucleus having odd number of protons, neutrons, or both, since they will have magnetic dipole moment. Though magnetic resonance imaging MRI is one of the few medical imaging modalities that does not deliver ionizing radiation dose to patients or staff, the strong magnetic field it generates can cause serious injury or death if not managed properly. The key thing that a patient should keep in mind is that one should never have any metals on their body while going for MRI. The use of MRI technology is always expanding in scope and use. Generally, using stronger stationary magnetic fields results in nicer MRI images. With the concept of better imaging, there has been 7 Tesla MRIs developed, which has twice the magnetic strength compared to 3 Tesla's MRI. Just because higher field strengths are available, however, does not mean that this is the optimal solution for every facility. This means that sometimes the patients have problem in that organ which can only be scanned at lower magnetic strength. Thanks.